Start again where we left. So what I'd like to do now is to show you how sometimes things can go wrong. And they can go wrong in two ways. They can go just wrong, and they can go awfully wrong. So, what's the difference between wrong and awfully wrong? If something goes wrong, you have the chance to fix it. If something goes awfully wrong, that's it. It's broken, there's nothing you can do. Okay? You cannot fight nature. Okay? And matrices come in that, square matrices, come in this kind of three flavors. Yeah? The ones which are really, really nice, like A in this example. Those which are nice if we do something to them. We have to fix them a little bit. Okay? And those which are hopeless. Nothing you can do about it. Okay? So let's start with some terminology. I'm going to keep this because I need it for my next objective, which would be to derive a recursive algorithm that tells this to you. But let's do on the side here a little bit of terminology. Actually, I'm going to do it on that board. Because it's kind of already written for me. So matrix A. So if A equals NU, for L, so the technical name for this is normalized lower triangular, or diagonally normalized lower triangle. Okay, so diagonally normalized lower triangular. Okay, so this is summation triangular. And U, let me rub all this rubbish away. So if A can be written as LU, often I forget my underlining. Okay, so it's your job to underline wherever it applies as you go through lecture notes. Okay. So when we have this kind of factorization, where L is diagonally normalized, lower triangular, and U is upper triangular, so I'm going to denote for speed, I'm going to denote this the set of upper triangular matrices in which are square by U or N, and lower triangular ones I'm going to denote them as L. In fact, L1. Okay? Because there's a slight dissymmetry. There's a slight dissymmetry between the two definitions because the lower triangular ones have the additional requirement that are diagonally normalized. So diagonally normalized means that they have ones on the diagonal. Okay? I'm not going to write the definitions, you can find them down in books. Okay, one thing is that we know what we're talking about. Okay, so if you really want to, okay, so let's write down the definitions. How would you write it very quickly? There's two ways of doing it. There's like the boring way and there's the quick way. Okay, so the quick way is recursive. It's a bit strange, okay, but sometimes getting used to recursive thinking, especially if you're a programmer, can get you in very far away places very quickly. Okay, so the way we define upper triangular is by recursion. Is like this. So an n by n matrix. So n by n matrix. U is upper triangular. If you can decompose it in the following form, you can write it as U, V, and W. Actually, that means U hat. Okay. And 0. Yeah, so. If you can write it like this, okay, so think of the matrix that we had here. Okay, so think of the matrix. I've rubbed it, okay, but you can imagine if you had zeros here, right? So how could that conform to that definition? Is this enough to write it like this? No. So this is just telling me that the first, so where this is a scalar, where U belongs to R, and V belongs to R, 1 times n minus 1, and of course the 0 here is the 0 hat. So let's put hats in smaller things, okay? So 0 hat is the 0 of R n minus 1, okay, the column 0, and U hat, of course, has to belong to be consistent with this, so this one belongs to R n minus 1, okay, plus 1, okay, but we don't usually write that, and this is n minus 1 plus n minus 1, okay? So I'm doing just the same procedure I did at the beginning of the lecture, of breaking down a matrix into blocks, okay? And these blocks here, raise this a bit. So these blocks here, this is any scalar, this is any row, whereas this one here has to satisfy a further property. It has to be itself upper triangular. Okay? So this is the recursive definition. It's a recursion on the dimension. Okay, because here I define what is upper triangular for Rn. And I'm using the definition of upper triangular for Rn minus 1. So it's like induction, yeah? Of course, for n minus 1, you have to do to n minus 2, and so on and so forth. So eventually, you're going to end up in the bottom case, or the base case. So you have to say what it means to be upper triangular in R. Okay? So you have to say where this guy here is also upper triangular. Okay? This upper triangular. And if n is equal to 1, all scalars are upper triangular. One by one matrices. It's a silly thing, but it needs to be said, right? So once you know that, then you can, let's check that this one here is an upper triangular matrix. So can it be written in this form here, with a 0 here? Yes, because imagine the red guys are zeros, okay? So I'm looking at this staircase guy with zeros here, okay? The new that I had written before the board, yeah? So this one here is actually upper triangular, right? Because according to this definition, right? All you need to do is to go through the definition, okay? So this one here is also upper triangular, and therefore this one is upper triangular. Okay, so basically you go back, where you check that each one is upper triangular. This one is upper triangular, this one here is upper triangular, this one is here upper triangular. Okay? Any questions on that? This is a strange definition. I want you to get used to recursive, okay? Because what I'm going to do next is going to be very recursive. Okay. Lower triangular and normalized lower triangular, same thing. It can be defined recursively. Okay? So in R, let's start from R. One by one matrices. What are the normalized lower triangular matrices? in 1 by 1 lower triangular matrices. Those are the ones that has 1 on the diagonal, and actually a 1 by 1 matrix is only one element, which is diagonal. So it means that the only element in the set of normalized lower triangular matrices of dimension 1 is 1, right? And then you go up, right? So you say a matrix is in N1 Rn if it can be written as follows. It can be written as a 1 here, a 0 row here of size n minus 1, some vector which I'm going to call m or l hat here, okay? L hat vector, and then L hat matrix here, okay? Where L hat is in the lower triangular matrices of size n minus 1. Okay, that's the one, that's the, if you want the recursive definition, and the bottom case is that L1 R1 is simply this guy here. Okay, let me rub a little bit of stuff. Okay. So I can remove all this stuff. So I can remove this stuff so I can read what we were. Okay, so where L belongs to L1 R. And here I have N1 R1 equals 1. So here you go. This is definition. Okay, it takes us a bit of time to do it, but it's worth doing because it gets us in a, it's kind of like block and recursive mood. All right, so let's come back to the statement here. So if A can be written as factorization of normalized lower triangular matrix and an upper triangular matrix, then we call it lucky. Okay, we call it lucky. You have to spell lucky like this. Okay, so the capital L and capital U. Okay, some people say it has an LU factorization. Okay, this is also known as an LU factorization. The longer version of lucky, okay, this is, which is short for it possesses an LU factorization. People are too lazy to say lower and upper triangular, okay, so they write LU, okay, for lower and upper, okay, so that's what it means, lower, upper triangle. Of course, lower is not precise completely because lower is, in this case, is normalized lower triangle. Okay, so there's lots of factorization of matrices, okay, this is the first one probably that you've seen. But there's many, many, many of them. Okay, so factorization of matrices is an important business. Okay, so this is what we call such matrices. We call them lucky. Then there are those matrices that can go wrong, but not awfully wrong. Okay, they are known in this jargon as plucky matrices. These types. Okay, so we have plucky matrices. Let's make an example. So example of a plucky matrix. Which is unlucky. So not all plucky matrices are unlucky. Okay, so in fact all lucky matrices are also plucky. Okay? But some of them are not lucky. I would call them unlucky. So An example is this one. Yeah? So let me write down example. Of course, matrices mean linear systems, etc. Okay, but I'm going to write it directly as a matrix before Gaussian elimination matrix. Okay, so in this case, I don't even do the right-hand side. Okay, I don't care about the right-hand side. The right-hand side of the system is something which we'll deal with later on. Okay, so now let's focus now on factorization. Okay, so by now we understand if we have factorization LU, then we can solve the system, no matter what the right-hand side is. Okay, so the right-hand side is something that can come in many different ways. Once you have the factorization, then you have a way, you have a recipe to invert your matrix. Okay, once you have the inverse of the matrix, you have. Okay, so the important part of the system is the, let's say, the hard part to solve is the left-hand side. Yeah, so basically matrix part. Okay? Good. So let's write down the matrix: 1, 1, 1, 2, 2, 5, 4, 6, 8. 4, 6. Okay, so this is the original matrix. So let's do this schedule there. Yeah, let's try and fit it. Okay. So what is the first row? The first row is 1, 1, 1. Okay, so that's easy. You just copy. Okay. Now for the second one, you have to multiply the first one by 2. And you have to multiply the first one by 4 to kill off this one and this one, right? So then you form this. This is known as the tensor product, or dyad. Okay. So how do you form it? You form it by taking these two elements and multiplying them with these two. Okay. So this is what you have to subtract from this one here. Okay. So basically, if you want, this is what you should do. You should do 2 minus 5 minus 6 minus and 8 minus. Okay, on the board it's really nice to do this. On paper it's a bit harder. Yeah? On the board you can route things. Yeah? And then you have 2 minus, and now you have to multiply 1 by 2. Okay, and then you have to multiply 1 by 5. Sorry. 2 times 1 is 2. Okay. And this one here will go away. Now we can keep it. Okay. We're multiplying 4 by 1, that's 4. And then we're multiplying 4 by 1, that's 4. Okay. So this, the way I'm doing it here, it's the way it's implemented on your computer. Okay, I'm behaving like a computer, and I'm using this as the memory. Okay? So I'm the CPU, this is the memory, okay? And I'm doing these calculations, okay? So here I'm storing what calculations I have to do, okay? But of course, if I were a true computer, I would write directly the result here, okay? Okay, so this is in my cache. So I'm using this as main memory and as cache, right? Okay, so now this is in my cache. Okay, so let me evaluate them. Okay, so 2 minus 2 is 0. 5 minus 2 is 3. 6 minus 4 is 2. And 8 minus 4 is 4. Now I'm in trouble, right? Because this is the new system. Okay? And I cannot Did I do something wrong here? I forgot to subtract the. Sorry. I had to do this, the calculation also here. Okay, so also here. Yeah, so this is, okay, but here I'm throwing the multipliers, that's why. Okay, so this is 0, 0. Okay, so that's correct. What I've done there is correct. Yeah. It's just this one is not the multiplier yet, okay, because I'm using it. So I'm going to put it on this, okay. Remember that I have to remove it before I finish the algorithm. But actually here I cannot even finish the algorithm because I have a 0, right? Okay, maybe I'm going too fast here. Am I going too fast, or is this okay for you? Would you be able to redo this algorithm in this kind of very concentrated way on this on the original example? Please do it. Okay, where you're using only one square, so you don't have to plot on the board the way I did with colors and stuff. You can really do it in one square, okay, by doing this operation every time. Yeah. Here we got stuck. Okay, why we got stuck? Because this 0 here is useless when I want to eliminate this one. So remember, this is 0. So the new system is this one. So maybe it's, I should write it. Okay, so let me write it. So the first step in Gaussian elimination provides this. Provides 0, 0, 3. 4, sorry, 0, 2, 4. So I'm confusing myself because I'm being so concentrated with my notation that it becomes very hard to see what's going on. Okay, so let's write it like this in order to understand what's going on. Okay? So basically what I did here is I multiplied this by 2 and I subtracted from this. Okay? So bang, bang, 3. Okay? I multiplied this by 4 and I subtracted it from this. Bang, 6 minus 4 is 2, and 8 minus 4 is 4. Okay? Everybody with me? Okay. So this was like the first, the reduction. This is also known as reduction. Okay, so I reduced the first column, or I eliminated like this, these entries here, right? I zapped them out by using Gaussian elimination. The problem is that I also zapped this one, which didn't happen earlier, because earlier we got the minus 8 there, okay? So these guys are known as the pivots, okay? So these are the pivots. So these are the pivots. First pivot, second pivot. So that's a pivot. These are the pivots of the Gaussian elimination. Okay? So that's what the P stands for. For pivoting. Yeah? So pivoting is what I'm trying to explain here. Okay? And it means this. It means once you get stuck like this, there's two alternatives. Either you're really, really stuck, or you can be unstuck. What's your take here? Can you be unstuck? Think about what we're doing. We're solving a linear system. Okay? So all we need to do here to solve the linear system, there's some right-hand side, okay, there. Doesn't matter, whatever this right-hand side is being manipulated in this right way. Yeah? The linear system is solvable, right? This is a triangular system, except I have to exchange two of the equations. Yeah, I just have to exchange the second equation with the third equation. Okay? So I have to undergo a bit of surgery. This matrix has to undergo a bit of surgery, and that's called pivoting. Okay? So let's write down here. So I'm transforming it. You can see this is a transformation, and there's another transformation. It's called pivoting. So once I pivot the matrix, then it's going to be okay. In this case, it was a very fortunate case that it's already going to be triangular, right? Because in 3D, in 4D, 5D, 6D, things they get more complicated because you might have not a triangular matrix. Okay, so you might have something which you still have to work on. Yeah, but then you recursively apply this plucky or PLU factorization algorithm. Okay, good. So that's one case where things can go right. Okay, so we pivot and we end up having 1, 1, 2, 4, 3. Okay, yeah. Solvable, everybody's happy. Okay, so that's an invertible matrix. Okay, so triangular matrices are very easy to spot if they're invertible. Invertible, remember, means that there is a -1 version of it that will hit it and make the identity. Okay? Said otherwise, it means that the map, because you see matrices produce maps, right? You take a vector, you apply a matrix to it, you get a new vector. That's a map, right? So that map there, if that map is invertible, then we call the matrix invertible. Okay? So invertible matrices represent invertible maps, which happen to be linear. Okay? So we haven't talked yet about linear maps, okay? But this is basically one of the reasons why it's important to understand linear maps. Okay? So we're coming back to linear maps tomorrow, okay? But now we'd like to understand Gaussian elimination per se. Good. So upper triangular matrices are invertible if and only if their diagonal elements are invertible. A number is invertible if and only if it's non-zero. Okay? For scalars, it's easy. You just look at the scalar. If it's a 0, you say you're not invertible. If it's not 0, it's invertible. The inverse is the reciprocal, algebraic, multiplicative inverse. Okay? Good. For matrices, it's not always the case. Some matrices are not 0, yet they're not invertible. Those are the horribly unlucky. They're unlucky and unlucky. They're losers. Yeah? They're losers of matrices. Yeah? And matrices do have losers. Okay, so that's one example for you. Let's write it down. So consider the system 1, 1, 1. We already saw 1 yesterday, okay, but I'm going to do another one here. So 1, 1, 1, 2, 2, 5, and this time we take 4, 4, 8. Yeah? So instead of having a 6 here, okay, we take a 4. Yeah? So when you're done copying that, I'm going to do it with a 4 here. Okay, so let's do it in column, so this way we don't have to. So let me put a 4. Okay, let me do the same procedure with a 4. So if I did this elimination with a 4 here, what I'm going to get is again a 0 here. Yeah. So I would get a 0 here, which means I would get a 0 here. And pivoting doesn't help, right? Because even if you exchange these two, you still get a 0. Okay? So that matrix is really, really bad. Okay? This is called a singular matrix. Okay? So this type of matrix is called singular. Okay? So of course I have to. Okay, that's it. It's very dramatic. Okay? Okay, that's a singular matrix. It's a singular matrix. Cannot be inverted. Cannot be inverted. So people call also singular matrices non-invertible. Okay, so non-invertible or uninvertible or ininvertible. Okay, so whatever. I always find that singular is much nicer to pronounce. Okay, so I use usually singular. Okay. The matrices that are not singular, some people call them non-singular. People like complicated jargon. I prefer to call them invertible because that's what they are. And it reminds me that if a matrix is not singular, then it has to be invertible. Okay, so singular and invertible are basically opposite one another. Okay, so singular is the opposite of non-invertible. And I usually don't like the words with non, something with non. So if I have a word that doesn't have non, it means the same thing, I prefer to use that word. It just looks a bit more positive. All right. So these are matrices. Now let's go through the algorithm, okay, and understand what we've done. Okay, so the way I'm going to do it is I'm going to start exploiting this idea of writing things blockwise. because it allows me to go really, really quickly. Okay, but as an advice to you is go through the examples, unravel this recursion that I'm going to write, okay, and do it in special cases, okay, because in that case you will see much more, you will learn much more about yourself. Okay, so let me do it here. I'm going to keep this one because I need it as a guiding principle. And before we do the full Gaussian elimination in a recursive way, let's do something a bit easier in a recursive way. Let's invert a triangular system recursively. So basically, let's produce a recursive implementation of back substitution. By the way, you guys know recursion, right? From programming. Yeah, that's the same guy I'm talking about. Okay, so recursive back substitution. So now this is a warm up. Okay, so this is. So suppose we have a recursive, a triangular matrix, okay, and we write it in this kind of blockwise way. Yeah? So the recipe is always write it in blockwise and then work your way from there. Okay? So with all the hats and the lines go underneath, etc. And we'd like to solve this for the following vector. I'm going to call it x hat. Fat x hat. And this must be equal to some right hand side, which we call f hat. Well, let me call it fg. Because f hat is going to have another purpose. Okay. How do we solve this? Back substitution. Well, remember, back substitution is like recursion, because you have to do it from the bottom, start from the bottom case. Okay, the bottom case is really a silly one. Okay, so the bottom case is the following: is ux equals f, where u and f belong to R. When is it you can solve this equation for x? So find x. Find x in R. So this, when is it you can solve this? It's when u is non-zero. I'm not going to say non-zero, I'm going to say invertible, even in a scalar case, because that's what it means, and also it connects to matrices. Whereas if I say non-zero, I'm going to forget that some matrices are non-zero yet not invertible. Okay, so I'm going to say invertible, which of course is the same thing as non-zero in R. Right? So if u is invertible, okay, so if u minus 1 exists, then what I do is I do u minus 1 times u minus 1. Okay, so here I'm going to respect also the order of multiplication. Why? Because at some point I'm going to move to matrices, right? And matrices don't commute in general. When you multiply two matrices, so A times B is not equal to B times A for matrices. For numbers, yes. But for matrices, we have to be careful. Okay? So let me respect that. There's nothing wrong with doing it with numbers. Okay? So we can all solve these systems without ever using the commutative law. This is nice thing, okay? Because they're really, really simple. Okay? All we have to do is to multiply, to pre-multiply the whole thing. Yeah? So we pre-multiply, and what we get x is equal to u minus 1 ux, and therefore this is equal to u minus 1 f. So I can solve the bottom case. Yeah? Good. So now let's do the recursion. So what does the recursion entail? Well, let's work in the same way, and then we're going to find out. So let me start with the first equation. Okay, so the first equation means ux plus rho v multiplying, which should be a hat. Yeah? So a hat multiplying x hat. Okay, the fact that everything has a hat means it's compatible. Okay, so I don't have to remember it's n minus 1, etc. But when I see it, I remember. Okay, so n minus 1, n minus 1. Okay, it's a scalar. And this one here is unknown. Of course, this one is also unknown. But I'm doing back substitution. Okay, so I'm going to assume that somehow I got x hat. Okay, so that's in my inductive assumption. Okay, that's my recursive ingredient. Okay, so assume x hat has been computed. Then all I need to finish my system is to compute this guy here, right? And that guy can be computed from the first equation, which says ux plus v hat x hat equals f. Okay? Which I can write as this one equals minus plus. Okay? So if x hat has been computed, then it's easy to compute that one because I do the same procedure I did there. I multiply the whole thing with u minus 1. Okay, so in fact, that's how I can solve this one. Okay, by doing x equals u minus 1. Okay? Of course, deriving it is neater than writing it like this, okay? Because when you write it like this, it's like a shock. Yeah? But you see where it's coming from. Okay? I did the steps. Okay. Then this one here is okay. And then I'm done. Right? Because I've assumed. So this is the magic of recursion. It always leaves you like, are we done? Is that it? Yes, that's it. Of course, when you say that x hat has been computed, okay, we're making an implicit assumption. We're making an assumption that this guy here has been inverted on x hat. Okay? Right? So in fact, if you want this to work for any entry, then you better assume that u hat is invertible. Okay, so this assumption is not a true assumption. It's just it was like an expedient to do this step here. Okay? But in fact, now I'm gonna remove it. Instead of assuming this, I'm going to assume that x hat can be computed as u minus 1 of what? U minus 1 of g hat, right? Because that's what it is, right? Because this one here times this column gives you u hat x hat equals g hat. Okay, so this is equal to g hat. Okay, so I don't need to assume x hat has been computed. Okay, all I need to do is basically algorithmically invert the steps. So this step comes first. Okay, so the first step you do is x hat equals u minus 1, and then you do this one here, right? So if you want the numbering in lines, then you do 1 and 2. Okay, remove this arrow. Okay, so what I'm going to assume is that u hat is invertible. I need this in order to perform the first step, right? And then I perform the second step. Of course, the first step is the one that opens the recursion. So opening the recursion means that when you go down to the next level, okay, you're opening, there's another floor. I have to go to n minus 1, yeah? And this is where it opens, okay? Because what does it mean to invert? In reality, this means, this is just like mathematical writing. And believe me, it is mathematical writing in most of the cases, okay? It's just mathematical writing. For solve u hat x hat equals g hat for in R minus 1. Okay, so what do I mean by mathematical writing? I mean, we just write this on paper. In your computer, you never, ever store. Well, sometimes you do it. Sometimes you do it, but it's a very bad idea. And if you can avoid it, you will avoid it. Everybody in the world, everybody sane in the world, does not store inverse matrices. I'm talking about large matrices. I'm not talking about like 2 by 2 and 3 by 3 and 4 by 4, the thing that you're doing in high school. Okay? I'm talking about these very large matrices that we use in practice. So in practice, our matrices have like millions, billions, quadrillions, zillions of entries. Yeah? They're too large. Okay? And inverting a matrix and storing it is really a big waste of space because you don't need it. Because every time you need the inverse is because you need it to be applied to some vector. So all you need is, in fact, is a vector. And a vector saves much more space than a matrix, right? Because a matrix is very fat. It's 2 by 2. I mean, n by n, right? Whereas a vector is just a slender n guy. Yeah? So you don't store it. Okay? All you need to do is to solve this. Okay? So in algorithmic parallels, what we're doing here, we're writing an algorithm. Okay, so let's call it back sum. Okay, so or rec back sum. Okay, so rec back sum, rec back sum. Okay, I'm going to write it in a functional way. So basically, I'm going to take its arguments, okay, and return something. Okay, so what are the arguments? The argument it takes is an upper triangle matrix. So it takes a U in U R n for some n. Okay, so n is, is part of the inputs. I should have done it before. Okay, but it's okay, right? And then also it takes the vector f. And returns. What does it return? It returns x such that ux is equal to f. Okay? And what does it do? It does this. It says, assume u hat is invertible, then do that. So basically it says, consider x hat to be the output of rec back sum. I told you it's recursive. Okay, so recursive means that the function is going to call itself, right? And here we have u hat n minus 1. Of course, there's some check that you need to do on the u. It's not always going to work. The buzzer will go off if u is not invertible. There are upper triangle matrices that are not invertible. It's enough that one of the diagonal entries is 0, you're screwed. Okay, so I have to add this in my check here. So this one here is invertible. Yeah, so u is invertible. But this invertibility is checked by the algorithm itself. Okay? So I have to put it at some point. Right? Where can I check it? Well, I'm going to check it here, because the next step is 2. So this was 1. Okay? The next one is 2. Is if, here's the if loop, right? If u is different than 0, then I do the inversion here, okay? Then define x to be u minus 1 minus b hat x hat plus and return, exit. Successfully, else fail. else failure. Right? So here's the failure, or the error. It says your matrix is not invertible. Please try again. Okay? Good. So this is a very simple. Do you have any questions? Okay, this is quite algorithmic. I hope this is quite clear to you guys how things work. Okay? So this is a very nice test counter for recursion. Okay. This was the warm-up. Big Daddy, Gaussian elimination. Okay, so let's take a moment, relax a little bit. Maybe we should keep this one. And let's do Gaussian elimination in the same pattern as we did the recursive backside. Okay. So I start from here, right? So I do the same. I play the same game as I played before. So I want to solve the system here. There's one thing I didn't tell you in this algorithm. Who is f hat? Did you notice that? Please tell me these things because sometimes I forget them when I'm writing something on the board. Okay? So let me come back to that. Okay? So it's very important for me to tell you what is f hat because I never told you what it is. Right? Well, f hat is that, but I have to say it. Okay? I have to. This algorithm is incomplete this way. Yeah? So it's, let's go first. So let me write the g hat here and come back to. This is what triggered my. I realized that. It's another advantage of good notation because the f hat plays the role of f in the small guy. Okay, that's the small f. But it's not coming from. It is coming from this one, but it's not exactly g hat. Okay, it's different. It's a g hat that is being manipulated. In fact, it's this guy here, which is, and the x hat is coming from, sorry, here. It is the g hat. In this case, it is the g hat. Yeah, so this is the lucky one. So f hat is equal to g hat. It's not going to be the same thing in the Gaussian elimination. That's why I got it. So this guy here equals g hat. Okay, so you plug in the g hat here because that's what's given. Okay, so the data is f and g hat. Yeah. So this is g hat. I should have written g hat. Yeah. Of course, in this case, the f hat is the g hat. It's not going to be the case here. It's going to be different. Right? But in fact, I don't even need to worry about that, right? Because remember, what we want to do is just an LU factorization here. And then I'm going to show you that if we have an LU factorization, inverting the L matrix is really, really easy. Okay? So instead of doing the whole thing, it's better strategies to even, again, divide and conquer. Okay? So we're going to divide this problem in two. We're going to factor the matrix, and then show how we can invert L. Why am I saying this? Okay, I'm saying this because the system I want to solve is this. And so let me re-summarize this in this very concentrated way. I want to solve this. And if I can write L, A, L, U, this is where thinking is very terms of groups and algebras and abstract things, becomes useful because it gives you the roadmap. It tells you where you're going to go before you get lost in this maze of indices and recursions and stuff. You know, you have to know where you're going. Otherwise, you're going to lose your way, and then it's very hard to get out of the maze if you don't know where you're going. Okay, so this is the roadmap. The roadmap is I'm going to factor A into this. Okay, that's going to be the first step. And now the step is to invert L. Okay, and then I'm going to do this. I'm going to do L minus 1 L dx equals L minus 1 F. So I need the inverse of L. I need to know how to invert lower triangular matrices. And you're going to say, well, just use forward substitution, right? Which is some kind of equivalent of backward substitution, except you start from the top. The easiest thing, you know. If I gave you a lower triangular system, it would be very easy. Okay, for example, if I gave you, I don't know, let's say 2, 3, 1, yeah? And this has to be, what is the solution to this? X equal to half, and y equals 1 minus 3 times x, 1 minus 3 half, that's minus a half. Solve. I don't even need to write it. It's so easy to do it that you don't even need to write it. It's actually easier because this 2 shouldn't even be there because I would have 1s. Okay? So in fact, inverting normalized lower triangular matrices is even easier than doing back rank. It's so easy that it doesn't even need an algorithm. There's a formula, there's a straight ahead formula for it, okay? We're going to derive it. Not now yet, not yet, okay? We're coming to that. Remember where L is coming from. L, in fact, is the inverse of what we did in order to do the LB factorization. Right? Because remember, what we did in the LB factorization was this. Let me finish this first. Okay? So let me just, so this is Qx, okay? And once I have this is going to be the F that goes into back rank. Okay? So let's review a little bit what we did from an abstract point of view when we did Gaussian elimination. When we did Gaussian elimination, we took the matrix A and we started transforming it by linearly combining the rows. Okay? Now, if you remember a little bit this matrix vector multiplication or matrix multiplication, what does it mean to linearly combine the rows? Yesterday we did linear combinations, which were very abstract things. Okay, but at some point I wrote you down a very kind of quick way of writing the linear combination of columns. I'm going to take a break in 10 minutes if you want. Okay. So d times lambda is basically this is the columns of V, which I'm going to call VI, okay, times the coefficients lambda I of some vector lambda. Okay, remember these are linear combinations? Yeah, linear combinations. Up to some m. Okay, so this was a linear combination, which is nothing but saying lambda 1, V1 plus lambda m Vm. Linear combinations. But these are linear combinations of the columns. Okay? So I think of the columns being the columns of the matrix, and I multiply a vector of coefficients in order to get the linear combination of these columns, which is yet another column which has been taken as a linear combination of those, right? What I want to do in Gaussian elimination is I'm working on rows. And this is the magic of the matrix notation. It has been designed in such a way that if you look at the matrix V, instead of looking at it as being a bunch of columns, look at it as being a bunch of rows put in a column. Okay, so let's think of another matrix, let's call it W, to be a rows. Okay, so think of it as being W1, and 2 is enough, right? So 2 by 2 is always the key. Yeah, so think 2 by 2 and I can do everything. Right? So suppose this is like a column like this. Then the coefficients must act from this side, from before. Yeah. So sorry, left, right, left. Yeah. So they have to act from the left. Okay. So if I want to take some combination here, I'm going to take some multipliers. Let me call them mu. We use a very nice name for multipliers. Okay. So I'm going to take a vector mu, but it's a row vector. Okay. So I have to transpose it. Let me transpose it. Okay, otherwise I'd have to write capital mu, but that looks like capital M, and then everything becomes quite confusing. Okay, so let me take a vector mu with coefficients. Okay, I'm going to transpose it, which means dot it, which means transform it into a row. Okay, and I'm going to multiply by mu. Okay, of course, if W is 2, then mu is also has 2. So mu t is something like mu 1 and mu 2. Okay? If you want, let's do a square bracket. And to be really picky with my notation, I'm going to assume it to be upper indexed. In fact, it should be lower indexed, but the transpose with upper indexed. I would have to create another letter. I'm not going to do that. Okay, so let's just look at this. So what it means that you have to pre-multiply your matrix in order to do the combinations of its columns. Okay? So basically, one step of Gaussian elimination is a pre-multiplication. Of the matrix. Basically what you do is this, is you start with a matrix A. Okay? In order to reduce it. Okay? At each step, you're pre-multiplying it by some matrix. Okay, so you pre-multiply by some matrix. Let's call it M for mysterious matrix. Okay, so we're going to pre-multiply by matrix M that will give us something of the form. So this one here is going to be a bit more upper triangular than this one here. So a bit more means it's going to be upper triangular only in the first step, like gamma. I call it the gamma. So the gamma is basically the gamma of a matrix is the top part. Yeah, top row and top column, or first row, first column. Yeah, that's the gamma. Yeah. So that one here has to be in the shape of an upper triangle, meaning it has to be of that form there. But the lower diagonal guy. These are known as diagonal entries of your matrix. Okay? So the lower diagonal matrix doesn't have to be upper triangle. But this one here is zeros. That's what Gaussian elimination does, right? So it transforms the matrix A into a new matrix, MA, by employing pre-multiplications, because now we realize with this little argument here that pre-multiplications are essentially linear operations on rows. Many of them, more than one. Okay? We're coming to that. I'm going to explain you why. Okay, this was like a quick preview of why you have to pre-multiply. Okay? So basically, operations on rows mean pre-multiplication. Linear operations. Linear operations on rows mean pre-multiplying or left multiplying, okay, left multiplying the matrix. And it's pre is very dangerous because pre-multiplying means post-applying because of the composition rule that goes backwards. Okay, but this is important thing to retain when you're running an algorithmic version of Gaussian elimination. Okay, so let's do it. Let's find what is this matrix M that we have subconsciously applied to A in the first step of Gaussian elimination. And then recursive is going to help us, because then we're going to realize that, in fact, we can build the whole matrix L by doing this successively. Okay? We'll come back to that. So for now, let's build one instance of M. Okay? So the first M. The M to reduce the first row. Okay? So let's index it. Okay? So because this is going to be a matrix, it's going to have two indices. Okay? It's going to be a row index and a column index. Okay? So I'm going to use the third index to indicate that this was the first one in the Gaussian elimination. So instead of doing yet another sub-index or yet another super-index, I'm going to use this bracket. Okay, this way I distinguish all the three indices one from the other. Okay, one is the row index, the other one is the column index, and this one is just the number in the iteration. When you're implementing Gaussian elimination, you don't see this counting here, okay, because you don't need a for loop for that. Well, you do, but actually that for loop is actually you're replacing the matrix over and over again, just as I did it on the board. Right? So the matrix they're fitting some kind of schedule like this. And so that's what you do when you're doing this elimination. And use this as a cache. Okay. But these are implementational issues that we don't need to kind of dig in yet. All right? Good. So this is, I think, a good point to take a small break. 5 minutes, but please be very, very quick. Okay, so this is just 5 minutes break for you to have a quick puff.